All right, students, these are the notes that were intended to be for Tuesday night. However, after watching how things went in class today, it's pretty obvious that we're having a whole lot of trouble with our problem solving, equation solving skills. So we will most likely spend another day in class on Wednesday continuing to work on those basic skills before we get to the more advanced inverses. So these will be the notes for Thursday's class, but if you want to go ahead and get them copied down and get ahead, that's completely up to you. Our objective for Thursday will be the student will learn more advanced skills process for discovering the inverse of an equation. Okay, more advanced skills process for discovering the inverse of an equation. Again, I anticipate these now being the notes for Thursday, October the 3rd. As always, press pause anytime you need more time, and then hit play when you're ready to move on. Now, the basic idea for solving an equation for a variable is that every operation has an opposite operation to undo it. This is how we are able to move things from one side of the equal sign in an equation to the other by constantly asking ourselves what is currently being done to that particular value, what is the opposite of that particular value, and if we perform that opposite operation to both sides of the equation, then we can move anything we want from one side of the equal sign to the other. Now, the problem is that some of the parent functions we have been studying have more complicated mathematical operators in them that we may not know how to deal with just yet. For example, logarithms. This is a new math operator to us. We're just beginning to learn what the graph does and what it's supposed to look like. The absolute value bars. I think we're pretty familiar with absolute value bars, but we may not be real sure how to remove them inside of a problem. And then, of course, you have the exponential equation down there on the right, and that one is new to us as well. We're just barely beginning to learn the graph and how it behaves and where it's supposed to be. Okay, so moving them around in an equation at this point in time would be a little bit unknown to us. So let's see if we can figure out what to do. Okay, let's say we're looking at an equation like this one. We'll start off with the absolute value bars. This is probably the most familiar of the three that we're looking at here. And our equation is a function h. If h of x is equal to the absolute value of x minus 2, find the inverse of function h. Okay, well, no big mystery. Doing the inverse is an easy thing. All we have to do is switch the variables. So instead of y equals the absolute value of x minus 2, the inverse we have x equals the absolute value of y minus 2. Okay. Now we're going to have a little bit of a discussion here. We've got to get to the y. Okay. And as we can easily tell, our y is tangled up inside of absolute value bars. We cannot get to y until we get the bars off of y. Okay. But how to do it? Okay. Now, here's the thing. When absolute value bars are wrapped around a variable in an equation, a new problem comes to the forefront. Okay? And that problem is this. The absolute value bars, by their nature, they are going to steal any negative value that tries to come out of them, because absolute value bars measure a distance. Distance is always positive. So the value of y minus 2 might be a positive number inside of there. But y minus 2 might also be a negative number inside of there. In either case, the absolute value bars are going to result in a positive value. So there's two different possibilities that end up in the same answer. We cannot ignore that there are two possibilities. We must pay attention to each of them. Okay? And since we have no way of knowing whether it's a positive value or a negative value, we must consider both possibilities, because there's two values for y that can make this a true statement. Okay, so here are the two possibilities: that x might equal a positive y minus 2, and that x might also equal a negative y minus 2. These are two very simple equations, but we have to consider both of them because they both might be the truth. All we're going to do now is we're going to solve these step by step until we get y isolated in both cases. Now the first step should be in the equation over on the right side. You can see that we have the negative of y minus 2. That means that everything inside of those parentheses has to feel that negative sign. So the negative distributes. We get x equals the negative y plus 2. Now, in both cases, we are looking at a situation where the variable y is loose in the equation now. It's free to be gotten to, but in both cases, we have a constant hanging on to it. So on the left side, we're going to add 2 to both sides of the equation, while on the right equation, we're going to subtract 2 from both sides of the equation. And they're getting different things done to the equations because of the different signs that are going on in each of the equations. But in both cases, the constant on the right side is going to be eliminated, and the one on the left is going to pick up x plus 2 on the left, and the one on the right is going to be x minus 2 on the left. Now the one on the left side is done. Y is isolated. The one on the right side is not done yet. We have a negative y. We do not want a negative y. We want a positive y. So basically what we need to have happen now is we need to flip the sign of the y. And the most straightforward way of doing that is to simply divide the entire equation by a negative sign or a negative 1. This will cause all of the signs in the equation to reverse, so we will end up with a negative x, a positive 2, and that will equal a positive y. Okay. Now, what to do with this? We have one answer coming, but two equations ended up being the answer. Okay. Well, here's basically what you do. We are going to combine them into a single answer, as is shown right there. The inverse of function h is a set that includes negative x plus 2 and x plus 2. Now, a couple of little side notes here. Okay, this is sometimes the case. Okay, sometimes it will be the case that an inverse will require two equations to describe it. This is called a piecemeal or piecewise function. Okay. Now, I'll get into the why of all of this at a later date, but for right now, just kind of understand that sometimes it will take two equations to describe a particular type of graph, and this usually happens when we have graphs that are not functions, and this particular inverse is not a function. It kind of for lack of a better way of putting it, it overlaps the top of itself so that there are x values that have more than one y. Okay. Now, what we're going to learn eventually as well is that these equations are going to have boundaries to them. Okay. And basically, the piecewise function, its main objective is to say that, hey, in one part of the domain, this function is doing this, but in a different part of the domain, it's doing that. Okay, so basically these equations, we will learn that there are boundaries inside of them, and one of these equations will carry the graph to a certain place, and then the other equation will take over from there. Okay, so we're going to learn about all that a little bit later, so we're kind of catching some glimpses of some things that are down the road. Okay, now that's the absolute value stuff. So we see how to do that. We have to break it down and look at the positive and the negative of what's inside the absolute value bars. But a couple of other problems that we've run into is that some of our functions are logarithmic and some of them are exponential. Okay, we do not know how to deal with this math yet until now. So let's see what we can do. Now, as I've already said, most things in mathematics have an opposite that will undo them. Addition undoes subtraction and vice versa. Multiplication undoes division and vice versa. Squares undo square roots, and there's 100 of these things, okay, these operations and their opposites. What we need to know now is that these two functions are basically opposites of each other. Okay, logarithms and a constant raised to an exponent are essentially inverse operations of each other. Okay. And if you look at the graphs, if you think about the graph of a logarithm and you think about the graph of the exponential equation, you will see that they are very, very similar. They both come from negative infinity. They both hug right along a negative axis. They both cross an axis at +1, and then they both radically change direction and head off to positive infinity. So they are doing very much the same things. They're behaving very much the same way, only their directions are different. One is pursuing the x-axis and then turns towards the y-axis. The other one's pursuing the y-axis and then turns along the x-axis. Just like with the inverses we are working, okay, their x and their y values are reversed. Okay, so logarithms and 10 to the x are opposites, and they will undo each other. So I'm going to introduce you to a couple of new basic rules here for how this stuff works in an equation. Okay, so I've got two different rules going on. This one on the left is going to be for when we have log of x or log of something inside of our equation, and the one on the right will be if we have 10 to the x or 10 to the something inside of our equation. Okay, for each of these equations, if the counterpart here is applied. Okay, for example, on the left-hand equation, it was log of something. Now here comes this base 10, okay, that is raising to the power of log of x. Okay, and on the right side, we're applying the logarithm to this base 10 raised to a variable. Okay, when you do these guys 10 to the log and log of base 10, these are natural enemies of each other. They cancel each other inside of a problem, and the result is that only the argument, as it's called, is left. Log of x, x was the argument, only x remains. On the exponential one, x was the argument, happened to be in the exponent. Okay, and after the logarithm is applied to it, only the x is left. Okay, that may be a lot unclear to you. We're going to look at a couple of examples, and then we will, of course, look at a couple more examples in class, see if we can't clear it up for you a little bit. Okay, first example. Here we have a function f of x. F of x is identified as equaling the negative of log x. Now, just for review, what does it mean that the logarithmic function there has a negative outside of the function? Okay, that is a negative sign that is not affecting x, it's affecting the entire side of the equation. That is going to turn this logarithm upside down. Okay, but anyway, we're supposed to take this function and find its inverse. Okay, well, rewriting it in inverse terms is easy enough. Inverse just means to reverse the independent and dependent axes. So we're going to have x equals the negative of log y. Okay, well, obviously the goal is to re-isolate y, so we need to get inside where the y is. Well, currently y is the argument belonging to the logarithm. Okay, so what we need to do is, first thing, I don't see any reason for us to continue to leave that negative sign in there. So we're going to send the negative to the other side of the problem. Okay, how can we change that sign? Well, again, just like earlier, we're basically going to divide the entire problem by a negative sign. That is going to reverse all of the signs. Log will now be positive, but the x on the left side is now negative. Okay. Now, log y, that is a single value. Okay, the operation logarithm and the y being the argument, they belong to each other. In order to separate them from each other, we have to do the opposite of the thing that we want to move. We are wanting to move the log, but leave the y. Okay, so what is the opposite of the logarithm of something? Well, the opposite is 10 to the x. Okay, so basically what we're going to do is we are going to apply 10 to both sides of the problem. 10 to the negative x on the left and 10 to the log of y on the right. This is just a mathematical operation. I know y'all don't understand exactly what it does to the problem or how it behaves or anything like that, but just understand that a base 10 and a logarithm are natural enemies of each other. They will cancel each other out. So what that's going to mean over on the right-hand side is the only thing that will remain is the y, because the base 10 and the logarithm canceled. 10 to the negative x, we do not know what this value is. Okay, we're not to that point where we can understand this numerical value, but it's not important that we understand it just yet. All we're doing is working the inverse and isolating y, and that's how it's done. Next example, here we have a function g, and g is identified as being 10 to the x minus 4. Okay, just for review, this is an exponential graph. Its base is a little higher. Okay, our amplitude is higher, so the graph will be in a bigger hurry to get going off to infinity. What is the x minus 4 going to do to the graph? Okay, well, we have a 4-unit phase shift attached to our x, and since the sign is opposite on phase shifts, that is going to move our phase shift over to the right. And we're instructed to find the inverse. Okay, well, once again, getting started on the inverse is no big deal. We reverse the positioning of the variables. So instead of y equals base 10 to the x minus 4, now we have x equals base 10 to the y minus 4. Okay, now here we go again. We're after y, but y happens to be in our exponent. We're going to have to get it down from there before we can work with it. So the question becomes, how do I get the exponent off of that base 10? Well, we need something that can cancel out base 10 so that our exponent will simply drop down into the problem. So what's the mathematical opposite of base 10? It is logarithm. So what we're going to do is we are going to take the logarithm of both sides of the equation. So now we have log x on the left, and we have log of base 10 to the y minus 4 on the right. Now this helps us because over on the right side, logarithm and base 10 are natural enemies of each other. They will cancel each other out, and in so doing, all we have now is the exponent drops out of being an exponent and it becomes the base itself, y minus 4. Log x is just a value. We do not know what this value is yet. It's just a value, just a number. Don't worry about it. Just leave it in there, log x. The only thing left for us to do is to isolate our y. There is no reason for the negative 4 to be hanging on to our y, so the opposite of minus 4 is plus 4. We'll add it to both sides. Log x is one kind of a number, plus 4 is a different kind of a number. So what we will do is we will allow them to remain apart from each other. Log x plus 4 is y. I've got a couple of more examples here. I want you to copy them down, and then we will take a look at them in class. If you're feeling like you maybe have a little bit of a hold on this, you may want to try to give them a shot, see what you think. First example, if function h is 2 times the log of x plus 3 minus 7, find its inverse. We have a logarithmic function. Its amplitude has been changed to a higher number, 2. Okay, so the logarithmic function is going to be moving faster than it should. We have a phase shift plus 3. That means it is moved 3 units to the left. And we have a vertical shift minus 7. So it's been dropped 7 units down. We'll work that out in class, probably on Thursday. And the final example is this one. Here we have a function j, and j is identified as being base 10 to the negative x plus 2, then plus 1. This is an exponential function. It has a negative x. What is the negative x going to do to the graph? The x-axis has been reversed, so our graph, instead of coming along the negative x-axis and then turning up in quadrant 1, it will come along the positive x-axis, running backwards, and turn upward into quadrant 2. Then you have the +1. Okay, that'll be a +1 vertical shift, moved 1 unit up. And I forgot about the phase shift. We got a +2 phase shift in there. That'll shift it 2 units to the left. We'll work this one on Thursday as well. Okay, it's going to take a little bit of effort on y'all's part, this solving equation stuff. It's pretty clear that we are not where we need to be, and we kind of need to get caught up. So if you are struggling mightily with working your equations, please do not continue to just show up to class hoping it will get better. You need to take some extra effort on your part to get caught up on things that you are already supposed to know. Again, these are the notes for Thursday. I appreciate you tuning in. I'll see you in class tomorrow.